So now we can talk about, just like in simple regression, fitted values, residuals are the two things we can talk about, and I guess goodness of fit, or let's just make that r squared. So we can talk about that. The concepts are going to be pretty well the same as simple regression, with just slight differences to account for the fact that we have more x's. So now an individual's fitted value, so this person, there's an I subscript, so the ith person's predicted value or fitted value is just the estimate for the intercept plus, the estimate for our first independent variable times that value, and so on and so forth. So this is a fitted value. We can do a residual for the ith person as well, and that equals the actual observed value for the person's dependent variable in the data set minus what their predicted value is going to be. So we could sub this expression for y hat into here if we want. So this is the residual. And notice that, I'll write this out in blue, if y hat I is greater than 0, that means yi is greater than y hat I, which means we've underpredicted y. And if u hat I is less than 0, that means yi is less than y hat I, which means we've overpredicted y. Though that should be fairly intuitive just from writing this out, right? And knowing that this is the observed value and this is the one predicted by our model. All right, so now we can talk about r squared and goodness of fit, which will be really similar to what we did before. So just like in simple regression, we have the sum of squareds total, or total sum of squares, which is the variation in y in our data set, in our sample. We have the explained sum of squares, which is the variation in our predicted values of y. And we have the sum of squared residuals, which is the sum of all of our ui's squared, ui hat squared, I should say. Because the mean of ui is 0 by definition, remember? And so remember, we can kind of decompose. I should make sure I keep the same notation. So the total variation of y in our sample is equal to the variation we're explaining through our regression plus the variation in that, plus the variation we're not explaining, so the variation in that residual. And just like before in simple regression, our r squared, or our goodness of fit, is equal to the explained sum of squareds over the total sum of squares, which we can kind of write two different ways. Either ESS over SST, which gives us the kind of the percentage of the total variation in y, which we're explaining through our regression. Or we can think of it as 1 minus the variation in y we're not explaining, or the variation, in the residuals over the variation in our y. I think that's a better way to think about it. Either way, you're going to get the same number. We're just mathematically playing around with these equations to go between them. And the interpretation is the same as it was before. So an r squared value tells you the percentage of the variation in y that you're explaining through your regression. A couple things to note is that or one thing to especially note is that it's never going to decrease as you add more variables. Or as you add more x's, I'll say. I mean, it's not possible to add another variable and explain less of the variation. Like, it's just not going to be possible. So this is another, so as we add x's, our r squared, the worst it's going to do is stay the same if we're not explaining any of the variation in y through our new x. But otherwise, it will go up no matter it's likely to go up no matter what.